Okay, so last time we built general purpose register. This time we will connect general purpose register to arithmetic logic unit to take some numbers from general purpose register and do some arithmetical logic operations on them through arithmetic logic unit. So let's do it. This is our arithmetic logic unit. It does operations, and this is general purpose register, which stores the numbers. They are connected inside the CPU. So what we're now going to build, I will click add circuit, and now we are building the actual CPU. Now we're finally doing the real thing. We have built all of those helper circuits like 8-bit adders and arithmetic logic units and so on. And now we're building the actual CPU, central processing unit. So inside the CPU, we take general purpose register, which is located exactly inside the CPU, and we take arithmetic logic unit. And arithmetic logic unit is actually located exactly under the general purpose register. So in this CPU, I put arithmetic logic unit and also the general purpose register. And I locate them one over the other so that because they are directly connected together. So, and if you put the inputs and outputs in the way that I recommended, A comes out from general purpose register bottom and goes right into arithmetic logic units input A, and output B goes into arithmetic logic units input B. Okay, so this is our first connection. General purpose register gives numbers to arithmetic logic unit, and arithmetic logic unit accepts two inputs. Next thing that we have is that the result from arithmetic logic unit would go out and go into general purpose register. However, things are not that simple. If general purpose registers would only get results from arithmetic logic unit, then how do you put new numbers into the general purpose register? So basically, general purpose register data input can accept data from multiple locations. So first, if we want to load a new number into register, we would need to take a number from flash memory that is pre-compiled, which says what number we want to get into some register, and forward it to general purpose register block. Secondly, we maybe want to take a number from random access memory. Thirdly, maybe we want to read number from arithmetic logic unit result. And finally, we would also want to read the status register, which is produced by arithmetic logic unit. So instead of just directly connecting arithmetic logic unit output to general purpose register, I will actually put a multiplexer here, which will be facing west. It will have, so select location could be, for example, top, so that we can easily connect the control signals from top, so that there's less signal crossing. Select bits, we would have 2, because our processor will have 4 different locations from which to take numbers and put them into general purpose register from flash memory, random access memory, arithmetic logic unit output, and from status register. So data bits will be 8 because we have 8-bit processor, and include enable will be set to no. So in this situation, I put arithmetic logic unit number into multiplexer's input number 2 counting from 0. So 0, 1, 2. This is where I connect arithmetic logic unit output. And multiplexer output goes into general purpose register data input. So data comes in and data goes out through these two lanes. So as I mentioned, now we can also put the status register next to arithmetic logic unit. It is a small memory register, which will be data bits will be only 4 because arithmetic logic unit only produces 4 flags. And the name of this thing will be, generally it's called SREG, SREG or status register. Okay, so this is output, which goes into data input, and Q is the previous values of status register, which go into arithmetic logic unit status register input. So this is status register in, and this is status register new values out. Okay, so as I mentioned, we want to read status register into the GPR to check out its bits maybe, or do some operations. So I would want to connect status register output also to multiplexer that switches between inputs from general purpose register. But our registers are 8-bit, status register is 4 bits, so we actually need to add 4 more 0 bits to this signal. To do that, we are using splitter, but not as a splitter, but the opposite way, as concentrator, I would say. So fan out is 2, but bit width in is 8. So now this thing automatically created inputs for bits number 0 to 3, which we can connect to status register, and bits for 4 to 7, which we will connect to a constant. So here under wiring, we have constant, which is 0, and data bits will be 4. So it's a 4 times 0, basically. And I connect it to bits number 4 to 7 of this splitter. Let's see how I can rotate them to take less space. Okay, so I want this thing to be facing north, south, probably south. So I connect 4 times 0, 4 bits of 0, to bits 4 to 7 of this splitter. And I connect status register to bottom for bit 0 to 3. And here out goes the combination of these two 4-bit nibbles, which is 8 bits, and I can connect it directly to general purpose register. So top 4 bits will always be 0, and bottom bits will be taken from status register. So for example, in status register, if I write F, which is 4 ones, then 4 ones go in, and here top part is just 4 zeros, so 4 ones is 15, or F in hexadecimal. Okay, now we also need to test our circuit and add some controls. So for example, we need to control arithmetic logic unit. To control it, we need 4 select signals to switch between 16 arithmetic logic unit operations. And it connects to arithmetic logic units of cell input. Next, we want to tell general purpose register 3 addresses: address into which register we want to save the data, which register to put on output A, which register to put on output B. So all of these signals are 3-bit signals. So I take this control box, I select data bits 3, and as I mentioned in lectures, address to write for simple cheap microcontrollers is always the same as address A. Okay, so we wouldn't have extremely many signals inside the processor. For convenience, when you select address A, it's going to be the same register to which the result will be stored. So address A and address for writing is the same number. So I can just copy the second control, which is address B. And then there are some control signals like write enable GPR. I'll put it here. Actually, I'll give them names immediately. So this box is address A and write. This will be address B. This will be, for example, write enable GPR. The next one is clock. So in this pin, I put clock. And finally, there is this reset input. So I'll put pin, from here, I'll name it reset. And I connect it to the reset input. And now also I will put two more inputs, which will be 8 bits. So I take this input, I select data bits 8, and the label will be value from flash, from program memory. It will be facing east. And the object will be facing west. So this thing, value from flash, facing west, 8 data bits, label value from flash, label location east, and we connect it to the first input of this multiplexer. This is how we give initial values to registers. And the second, actually, I can just copy this and name it value from RAM, random access memory. This goes right here. So we can take value from flash, from RAM, from arithmetic logic unit, or from status register and use it. So a status register also requires clock. Well, the clock will be the same clock as for general purpose register. So I will carefully connect them together right here. And this clock is used to know when to update the register. So there's also status register enable. Well, we would want it to be enabled for writing only when we do arithmetic logic unit instructions. So with this, we can also control when to update status register. So I will create a new input, which will be called status reg update, or status register write enable. Which I will locate, for example, here. So, in some instructions that use arithmetic logic unit, we want to update status register. But in an instruction where you read a value from random access memory, you want status register to not be updated. So status register write enable will be low. And only when we do arithmetic logic operations, we should set this bit high and then update the value. And status register also has reset input. So when we start up our processor, we actually want status register to also reset. So the status register line, which is called clear, I will also connect to reset signal. So let's check out. So when I click reset, status register was reset. Okay, so now let's check out if we have some problems with these numbers. In. So I will save my work and let's try to use this. And also another input, of course, is general purpose register source select multiplexer. So with this signal, we select from which location to take a value and write into general purpose register. So we create another input, and since we have 4 inputs, we need 2-bit number to control all of them. So data bits are 2, and this will be called the GPR source select. Okay, now this thing should work. In a second, maybe there's some error. So I'll try to close and open this project. Okay, so I closed it, I opened it, and the red errors disappeared. So maybe it helps. Now I want to, first of all, reset the CPU. Okay. And now using this hand tool, I can peek into general purpose register initial values. So we can see that all of them are 0. Now let's say I want to write a number inside some register. So I want to write number 5, which is, for example, 101 from flash memory into general purpose register number 2. So I select address for writing number 2, counting from 0, value from flash, I set 5. I set general purpose register select to 00, which is flash. I can click on this line and I see that this 5 is already forwarded to general purpose register. To write into general purpose register, I need to set write enable general purpose register high. And as you can see, status register write enable is low because we're writing into it, we're not doing something else. Also, we give this thing a name, ALU of cell. Okay, so now we have input the number. It goes into general purpose register. We switch on write enable. We select which register we want to write. Address B bits don't care. You can select any, it will not have any effect. And now when I click clock rising edge, the value is stored into register R5. As you can see, this 5 is going into all registers, but only register number 2 is selected with address right, and on rising edge, register R2 value is updated to 5. And I click clock low, and it's done. Okay, let's do it again. Let's say that I want to read the value from RAM, value number 6, for example. Here is 6. And I want to write the value into register number 3. So address right, I select as 3. General purpose register source, I select to input number 1. So now value from RAM 6 is on input number 1. So I select here 1. It is forwarded immediately through this multiplexer into general purpose register. I keep write enable high, and I do again clock rising edge, falling edge, and number 6 is written into register R3. Let's say I want to add, let's say I want to subtract register R3 from R2. So I wanted to do the 6 minus 5. So 5 is in register number 2, and I want it to be on address B. So on address B, I select number 2, and general purpose register immediately outputs 5 on line B. And register number 3 is selected here, and its value 6 is forwarded into arithmetic logic unit. We want to keep write enable high because we want to write the R3 minus R2 into general purpose register. Then we want to select operation. Subtraction is operation number 5. I just remember it from the head. So it is 5. And since arithmetic logic unit is not clocked, it immediately gives you the output number 1 because 6 minus 5 is 1, and it's forwarded here. So to store it into general purpose register, we also need to set general purpose register source to input number 0, 1, 2. And as you can see, it's forwarding this number 1 into general purpose register. And remember the convention, write register and address A register is the same. So when I do clock rising edge, falling edge, the result is written into register A. So register R3 was received an operation 6 minus 5 is 1 written back into register number R3. I told you this about this in the lecture, so you probably remember. Okay, so this is how we have created a general purpose register and arithmetic logic unit connection inside the CPU. We're now building the actual CPU. And now you would want to ask, well, how are these values written in the flash? Well, they're written in the flash when you write your code. For example, let's say in your code, I will write a C programming language pseudocode. But basically, when you write, for example, in C programming language, x equal to 5, what it actually is translated into is assembly line. So a compiler automatically gives X some reserved location in memory or in registers. Let's say X is stored in registers for simplicity. And compiler automatically selects that, for example, number X will be stored in register R2. So what compiler does is it generates assembly language instruction, which is load load into register R2 number 5. So there is assembly language special instruction called LDI, which just copies a number into register. You give the register number and the number to copy. And this instruction is immediately translated into a machine code. So assembly language instructions translate into machine code. So LDI basically says how to set all of these control signals. And in our simple microprocessor, it has code, for example, 0010. Let's say it's LDI. I don't remember which one is it. Next 4 bits tell you which register to select for writing. So register number R2 would be number 2 in binary 0010. And then the final 8 bits would be this number 5. So number 5 is 00000101. And now this is one instruction inside of your code, one machine code, one line that a processor processes. And basically, these bottom 8 bits are just directly wired to this multiplexer's input number 0. And these 3 bits are just directly wired to address A and address for writing. And the rest of the bits are used in a lookup table to control general purpose register select signal, clock, reset, ALU op select, write enable general purpose register, status register write enable, and so on. So it's just hardwired. The wires from your flash memory instruction just go directly to general purpose register input selector. And this is how these numbers are loaded into your processor. I hope that it became clearer, and we will actually do it more in the labs. So this is all for today. We connected general purpose register to arithmetic logic unit. We created 4 different inputs for general purpose register data, 4 different sources: flash, RAM, ALU, and status register. And we can also do some operations, and the result will be written into general purpose register if we set all of these control bits correctly. But you don't have to worry. We will actually create a block that automatically sets these signals, and you don't have to really worry about them or making some mistakes. In processors, it's done automatically, as I said, based on the first bits of the instruction through lookup table. But that's a topic for the next lesson. So thank you for doing this lab, and bye.